Welcome all to YouTube channel Mechanical Study, where we study different mechanical systems. Today we are going to start with the new subject series, that is subject which is called as refrigeration and air conditioning. We already started subjects like fluid mechanics, then internal combustion engine and thermodynamics. So today we are going to start with the refrigeration and air conditioning series, where we will cover different multiple choice questions which will be asked in engineering service exam, then GATE exam, then SSC JE exam, or RRB JE exam, or different state examinations. So here today we are going to start with the question number 1 for subject refrigeration and air conditioning. So basically here first question, that is the ideal gas refrigeration cycle is the same as the, so here options are Breton cycle, then next reverse Breton cycle, vapor compression refrigeration cycle, and last is the vapor absorption refrigeration cycle. So ideal gas refrigeration cycle, which is also called as the reverse Breton cycle, or which is also called as Bell-Coleman cycle, which is nothing but a reverse Breton cycle. It is called as ideal refrigeration or ideal gas refrigeration cycle. Here a reverse Breton cycle or Bell-Coleman cycle can be drawn on PV diagram like such, where this will be the cycle, that is 1, 2, 3, 4. If I draw it on a PV diagram, so 1 to 2 is a reversible adiabatic compression, 2 to 3 will be the constant pressure heat rejection, then 3 to 4 will be the expansion, that is 3 to 4 process with the reversible adiabatic expansion, that is process 3 to 4, and 4 to 1 is the heat addition process. So this is the all about the Bell-Coleman cycle, which is also called as a reverse Breton cycle or a ideal gas refrigeration cycle. The next question, 1 ton of refrigeration is equivalent to, so what is 1 ton of refrigeration? So 1 ton of refrigeration is nothing but, it is equal to nothing but the amount of heat that is removed from an ice at 0 degree Celsius in 24 hours to convert it into water, or a reverse phenomena, that is the amount of heat that is extracted from water in 24 hours at 0 degree Celsius in order to convert into ice. So here latent heat of vaporization of ice is nothing but 335 kilojoule per kg. So here by definition of terms of refrigeration, it can be written as, that is the amount of heat that is removed from the ice at 0 degree Celsius in a 24 hours. That is considering a 1 ton of ice at 0 degree Celsius, and the latent heat of vaporization of ice is nothing but 335 kilojoule per kg. So here this will be divided by 24 into 3600, so that converted into kilojoule per second. So here final answers comes out to be 3.5 kilojoule per second per kilowatt, that is the 1 ton of refrigeration, and that is also unit of refrigeration. So here 3.5 kilojoule per second, or it is also written as 210 kilojoule per minute of turns of refrigeration. So here basically unit according to the options, that is option A is 336 kilojoule per minute, option B is 210 kilojoule per minute. So here option B will be the right answer, that is this is a unit of a refrigeration, that is 1 ton of a refrigeration, that is equivalent to the 210 kilojoule per minute, which is also called as a refrigeration capacity. It is also called as a refrigeration capacity. So here there are two terms, there is a refrigeration capacity and a refrigeration effect. So here refrigeration capacity, that is generally measured in kilowatt or in kilojoule per second, and refrigeration effect, that is measured in kilojoule per kg, and the relation between refrigeration capacity and refrigeration effect is nothing but refrigeration capacity is equal to mass into refrigeration effect. So here this is the relation between the refrigeration capacity and refrigeration effect. The next question, which of the following is true for reverse Breton cycle? So the options are, it is a very low COP relative to vapor compression cycle. B, it consists of two constant pressure process and two isentropic process. C, its working fluid is generally eco-friendly. D, heat transfer in evaporator is at constant temperature. Here we will see first of all the reverse Breton cycle or a Bell-Coleman cycle. Earlier I have told you that. So it consists of four processes, that is 1 to 2 is the reversible adiabatic compression, 2 to 3 is the constant pressure heat rejection, 3 to 4 isentropic heat isentropic expansion, and 4 to 1 is the constant pressure heat addition. So here in option, the option given, that is option D, heat transfer in evaporator is at constant temperature. It is not true, because in case of Bell-Coleman cycle the heat addition takes place, or heat transfer in evaporator is take place at constant, that is constant pressure. Here pressure will be constant. So here that is not the correct answer. So option D will be the right answer. Then question number 4. An ideal refrigerator has a capacity of 6 tons. With COP of 6, the capacity of the prime mover to run the machine should be at least. So first of all, consider case of an ideal refrigerator. Suppose there is a refrigerator, so it is a capacity of 6 tons. That is, here it has a capacity of 6 tons. So here one can write down that is, suppose I am considering the case of a refrigerator. So refrigerator is a device where it extracts heat from low temperature reservoir. Suppose I am considering this is a T2 T1 temperature, and give it up to a say higher temperature reservoir, which is a T2, with some external work add. So here the refrigerator has a capacity of 6 tons. So here the refrigerator capacity is given, that is of 6 tons, and its COP is also given. So here the coefficient of performance of a refrigerator is nothing but the refrigeration effect to the, that is the work input, power input, that is work required to drive with the compressor. So here COP is 6, then refrigeration capacity is given over here. So it is nothing but 6 into, that is 1 tons is nothing but 3.5 divided by, that is the power input that we have to find out. So here just this comes out to be 3.5 kilowatts. So here option B will be the right answer. The next question, a Carnot refrigerator works between temperatures of 200 Kelvin and 300 Kelvin. If refrigerator receives 1 kilowatt of heat, the work requirement will be. So here questions are the Carnot refrigerator. So here one should know about the Carnot refrigerator. So COP of a Carnot refrigerator is nothing but, that is, suppose I am considering Carnot refrigerator working between the, suppose TH is the higher temperature, TL is the lower temperature, and it is the external work done. So here the COP of a Carnot refrigerator is nothing but TL upon TH minus TL, or suppose this is a heat transfer from the lower temperature reservoir, and this is the heat transfer to the higher temperature reservoir. So here this can be written as, or it is equal to, that is QL upon QH minus QL, or W in, that is work done. Okay, so here final equation that can be written as, in order to calculate the required work input, so here COP can be written as, that is, so here we have to find out first of all with the help of a COP formula. Here the question, first of all you have to find out the COP, that is equals to, that is TL upon TH minus TL, which is given over here. So TL is 200 Kelvin, TH minus TL is 100, so COP becomes 2. So COP will be 2. Once you know the COP, so COP will be equals to, that is QL upon work input. So here work input is, here if the refrigerator receives 1 kilowatt of heat, means QL will be the 1 kilowatt. So here work done will be equals to, that is to value which is nothing but, here QW is COP is 2, so here QL is 1 kilowatt, so this comes out to be 0.5 kilowatt. So work input will be the 0.5 kilowatt with COP 2. COP equals to 2. So here option A will be the right answer. Then next question, the efficiency of Carnot engine is 0.75. If the cycle is reversed, COP of a reverse Carnot cycle will be. So first of all, you must know that the COP of a heat pump is reverse of efficiency of a engine. Means efficiency of the engine is 0.75. That means whatever the reverse Carnot cycle will be, reverse Carnot cycle means it will device will be works like a heat pump. So here its COP will be equals to, that is heat pump COP will be equals to 1 upon 0.75. This will be the correct one. So it is comes out to be, so on to simplify this, it is comes out to be final value. These options are 1.25, then 1.33, then 1.75 and 1.95. So here 1.33 will be the right answer, that is option B, that is equals to, that is 1 upon 0.75, that is efficiency COP of a heat pump will be equals to 1 upon 0.75, which is nothing but the efficiency of a heat engine. Okay, so COP of a heat pump will be the reciprocal of efficiency of a heat engine. And if they ask to find out the COP of a refrigerator, COP of a refrigerator, so it is nothing but the COP of a, there is a relation between the COP of a heat pump and COP of a refrigerator is nothing but COP of a heat pump minus COP of a refrigerator equals to 1. So here the COP of a refrigerator will be equals to COP of heat pump minus 1. COP of refrigerator heat pump minus 1. So this will be the COP of a refrigerator. Next question, that is COP of a reversible heat pump is 1.2. If it is run as reversible heat engine, then its efficiency shall be. So here again it is a reciprocal, that is COP of a heat pump will be equals to 1 upon efficiency of a heat engine. So here efficiency of heat engine will be equals to 1 upon 1.2. So correct answer will be 0.833, that is option A will be the right answer. The next question, which of the following is not true for heat pump? So basically heat pump is a device where, so heat pump is a device where a desired effect will be occur at a high temperature side, that is at higher temperature, means the surrounding will be at a lower temperature, and the desired effect where the desired effect that is occurs at the higher temperature side here. So here its COP will be equals to TH upon TH minus TL for a reverse heat pump. So here number of options are there. So here first option is low temperature reservoir is environment, so it is correct. Then next, low temperature reservoir is conditioned space, so it is not true because high temperature reservoir is conditioned space. It is a cyclic device, it is a true. Then work done is negative, again it is a true. So here option B will be the right answer, that is low temperature reservoir is a conditioned space. So here that is a high temperature reservoir will be the conditioned space in case of a heat pump. So option B will be the right answer. Here they ask about the not true statement. Okay, means what is a false statement? So false statement is that low temperature reservoir is conditioned space. The true statement will be the high temperature reservoir will be the conditioned space. Okay, in case of a heat pump. And in case of a refrigerator, in case of a air conditioner or a refrigerator, the low temperature reservoir will be the conditioned space and high temperature reservoir will be the environment. So here next question, for this question correct answer will be option B. Then next question, a Carnot cycle operates between temperature of 727 degrees Celsius and 227 degrees Celsius. The efficiency of engine is, so here for a Carnot efficiency, that is nothing but the, for an engine its efficiency is nothing but the W net or work done upon heat supplied, or it can be written as TH minus TL upon TH, as it is a reversible cycle. So these two value will be same. So here they ask about the efficiency. So here the efficiency can be found out, that is TH is 727, TL is at 227, so you just put in the formula. You just convert it into a Kelvin, that is 727 plus 273, that is nothing but the 700 plus 200, that is 1000, minus 227 plus 273, so it comes out to be 500 divided by 1000, so it comes out to be 500 by 1000, so it comes out to be point, that is 1 by 2, that is 0.5, that is 50%. So here option B will be the right answer for this question. So option B will be the, here we can see the option B will be the right answer. And the next question, question number 10. A reverse Carnot engine is used for heating a building. It supplies 210 into 10 to 3 kilojoule per hour of heat to the building at 20 degrees Celsius. The outside air is at minus 5 degrees Celsius. Heat taken from outside will be nearly. So this is the question. So here the questions are: the reverse Carnot engine is used for heating a building, means a reverse Carnot engine that is work like a heat pump where it is used to heat the building. So it is a heat pump. Okay, it supplies heat to the building at 20 degrees Celsius. Building which is at a 20 degrees Celsius, it is a higher temperature, and lower temperature is that which is at a minus 5 degrees Celsius. So here heat supplies is 210 into 10 raised to 3 kilojoule per hour. Okay, and they have asked to find out the heat taken from the outside will be nearly. So here W in, this will be the W input, then this will be the Q supplied. So this is the thing that they have asked. Okay, so to find out this, we must know the formula for the same. Again, so use the same formula, that is COP will be equals, for heat pump COP will be equals to the, that is the heat supplied, that is nothing but 210 into 10 raised to 3 upon W input, that is not known to us, but it is a reverse Carnot. Okay, so this can be found out. COP first of all can be found out, that is equals to the TH upon TH minus TL. So here TH nothing but the 20 degrees Celsius, so it is nothing but 293 Kelvin. Okay, upon TH, that is 293 minus 273 minus 5, so it is comes out to be 268. So put in those, we will get the value of COP. Put this in the this equation, we will get the W input, and it is comes out to be, sorry, if you put this in the this formula, we will get the W input. Once you find out the W input, so W input is nothing but, or power input is nothing but the formula for that is Q. That is Q here from the suppose this is a heat pump, out of which, just a minute, suppose this is a heat pump, out of which Q2 is supplied to the high temperature reservoir, Q1 is extracted from the low temperature reservoir. Okay, so for that W net will be equals to, that is, suppose this is W. Okay, so here W net will be equals to Q2 minus Q1, because Q1 plus W will be equals to the Q2. Okay, so once you find out W net, we will get the, that is put that as you all know the value of Q2, that is nothing but 210 into 10 raised to 3 kilojoule per hour. We can easily find out the Q1, and it is comes out to be 192.08. So here option A will be the right answer for question number 10. Next question: a cold storage is to be maintained at minus 5 degrees Celsius while the surroundings are at 35 degrees Celsius. So here this is a question of a cold storage. Okay, so here cycle will be the refrigeration. Okay, or we can consider a case of a refrigerator. Okay, the heat leakage from the surroundings into the cold storage is estimated to be 29 kilowatt. The actual COP of refrigeration plant used is 1/3 of the ideal plant working between the same temperature. The power required to drive the plant will be. So here given is that the actual COP of a plant is 1/3 of a theoretical COP. 1/3 of a theoretical, that is actual is 1/3 of a theoretical. And here just we are going to draw first of all the diagram, that is for the refrigerator or ice plant. Here the low temperature reservoir is maintained at a minus 5 degrees Celsius. Higher temperature reservoir is maintained at a 35 degrees Celsius. Okay, diesel effect will be occurs on this side. The heat leakage from the surroundings into the cold storage is estimated to be 29 kilowatt. Okay, so here this will be the 29 kilowatt, that is Q1 will be equal to here 29 kilowatt. So here W input will be here. So here actual COP will be the 1/3 of the theoretical COP. So here first of all you should find out the theoretical COP. For that purpose you should know the two temperatures. Once you know the two temperatures, it is quite easy to find out the same. So here the actual or theoretical COP, that is comes out to be just to find out the theoretical COP is just out of put, that is a TL upon TH minus TL. So it is nothing but minus 5 plus 270, that is 268 upon 35 plus 273, that is nothing but 273 plus 35, that is 308 minus 268. So it is nothing but 268 upon, so it is 308 minus 268, that is 0, that is 40. So it is 260 upon 40. So this will be the COP theoretical. Once you find out the theoretical COP, it is quite easy to find out the actual COP, because actual COP is 1/3 of the theoretical COP. Once you find out the that is actual COP, because this will be the COP actual will be the 1/3 of the theoretical COP. And once you find out the actual COP, which is comes out to be 2.233, it is quite easy to find out the power required to drive the plant. So that will be the equals to COP actual will be the, that will be the Q1, that is the desired effect, which is at a lower temperature side, upon, that is W input. See here W here COP actual, to find out COP actual, here the given is that the heat leakage from the surrounding is the 29 kilowatt, and this is nothing but the Q1. So here put that value of 29 kilowatt in this equation. COP actually is 2.233. We'll get the find out W is equal to 29 upon 2.23T. So it is comes up to be approximately. So I think it is comes out to be nearly about. So here we can see the answer, that is 12.98 kilowatt. That is approximately comes out to be 13 kilowatt. Okay, so it's just we have to put that the in the equation, that is nothing but P or COP will be equals to Q1 upon W or power input. So here Q1 is 29 divided by that value, that is we already calculated COP actual 2.233. So we will get the final answer, that is 12.98 kilowatt. So option D will be the right answer for question number 11. The next question, ice is formed at 0 degrees Celsius from water at 20 degrees Celsius. Temperature of the brine is -8 degrees Celsius. The refrigeration cycle used is perfect reverse Carnot cycle. Latent heat of ice is equal to 335 kJ per kg, and CPW, that is specific heat of water, the ice formed per kilowatt hour will nearly be. So here that is ice is formed at 0 degrees Celsius, that they have given, from water at 20 degrees Celsius. Temperature of the brine is -8 degrees Celsius. The refrigeration cycle used is perfect reverse Carnot cycle. Latent heat of ice is also given. So first of all here we have to find out the Q refrigeration. So to find out the refrigeration effect, first of all you must know the, here the latent heat of ice is given, that is 335, okay, into, that is M into HFG. So here into mass of ice plus the amount of heat, that is sensible heat loss from the water, which is at a 20 degrees Celsius. So here to refrigeration effect comes out to be 335 into M plus MCP, that is latent heat loss from the water, which is at 20 degrees Celsius. Okay, so here mass is not known to us, that we have to calculate, into CP, into CP is known to us 4.18, and it is cool from 20 to the 0. So this will give us a Q refrigeration in terms of mass. So here once you find out the ideal COP, so which can be find out with the formula, that is COP ideal, that is TL upon TH minus TL. So this can be TL can be taken as minus 8 degrees Celsius. Okay, this is the temperature which is at the lower side, that is the brine temperature as minus 8 degrees Celsius plus 273 divided by TH which is at 20 degrees Celsius. Okay, so here this can be written as 265 upon, that is 273 plus 20, that is 293 minus lower side temperature, that is minus 8, that is 265. So put this and we will get the ideal COP, ideal COP which comes out to be, here we can see the 265 by 20, the COP ideal. Okay, so once you find out the refrigeration effect, you just have to find out the COP, that is we have to find the power input. So COP is nothing but the refrigeration effect upon the power input. So if this comes out to be, that is COP 265 by 28, refrigeration effect we already know 35 into mass plus 4.18 into 20 into mass divided by power input, which is nothing but the, so here the ice is from per kilowatt hour. So here that is ask is to per kilowatt hour. So here just we have divided it by 3600 because we have to find out it by per kilowatt hour. Okay, so it just divided by 3600, you will get the answer in a power that input, that is in a per kilowatt hour. If you now divide it, we will get the answer in a, that is in that is kilojoule per second per kilowatt. Okay, but they have asked if you not divided by 360, we will get the answer in kilowatt. Okay, so because here we are dividing with the 3600, so that is the reason I will get the answer in kilowatt hour. So here final answer comes out to be 81.4 kg. So here it will be formation of 81.4 kg of ice from the above setup. Okay, so here option A will be the right answer. So this is all for today. I hope you all enjoyed today's lecture. So to like and subscribe to our channel and share with your friends so that they will also get advantage of our channel. Thank you. Once again, do like and subscribe to our channel. Thank you.